Noche cósmica.
Imagine a world where water never freezes solid, where an entire ocean churns beneath a coffin of ice, separated from the vacuum of space by a shell so thin it would crack under your fingertip. Somewhere out there, in the cold reaches beyond Jupiter, this world exists. And yet we barely knew it was there until very recently in the long history of human observation. The question that drew scientists across billions of kilometers was simple and profound. How could such a place exist at all? Consider the scale of what we're about to enter. Saturn itself is a planet so vast that 1,000 Earths could fit inside it. Yet it hides something even more remarkable in its slow waltz through the solar system. Around this gas giant, dozens of moons orbit in a cosmic ballet so intricate that understanding even one requires patience, precision, and a willingness to listen to what the evidence whispers rather than shouts. Most of these moons drift in silence, cratered and ancient, their stories written in impacts and stone. But one of them, small enough that you could drive across it in an afternoon, yet large enough to harbor secrets beneath its scarred and brilliant surface, has begun to reveal something that changes how we think about where life might flourish in the universe. If you find yourself drawn to these quiet corners of our solar system, to the slow unfolding of mysteries that orbits billions of miles from Earth, I invite you to subscribe for more meditative journeys through the most relaxing facts about Enceladus and the hidden wonders that patient science continues to unveil in the darkness. Each story we'll explore together moves at the pace of discovery itself, unhurried, thoughtful, grounded in real data, yet alive with the sense of wonder that discovery still deserves. Now, picture the night side of Saturn. Not the sun-facing edge where light spills across the gas giant's layered atmosphere in shades of gold and deep amber, but the dark hemisphere where light is merely a memory. Imagine the absence of warmth there, the profound cold that settles across the void. In this darkness, a small sphere drifts. It is not perfectly spherical. Gravity has pulled it slightly out of true, and its surface is battered with the scars of 4 billion years. But there is something almost ethereal about this moon as it moves through the shadow of its parent planet. Its surface catches starlight and throws it back with an intensity that seems almost defiant against the surrounding black. It gleams like a pearl suspended in ink, turning slowly, quietly, as though it has all the time in the universe, which, in a sense, it does. This moon has a name, though it was not called by that name for nearly 2 centuries after humans first glimpsed it through a telescope. It is Enceladus. And the question of what it truly is, what lies beneath its brilliantly reflective shell, held science in a patient grip for generations before the answers began to emerge. To understand Enceladus is to understand something about the nature of hidden worlds themselves. It is to recognize that the solar system we inherited from the discoveries of the past century is far stranger, far more intricate, and far more potentially alive than earlier astronomers ever imagined possible. The moons we thought were dead and inert began to whisper their secrets. The places we deemed too cold, too dark, too hostile to harbor anything resembling what we call life, started to reveal signs of warmth, of movement, of something stirring beneath the surface. The journey toward this understanding began with a simple act of observation, and it continues even now, guided by instruments that cross the void at speeds that would obliterate anything they touched, and by scientists on Earth who listen intently to the faint electromagnetic whispers these distant messengers send back. Yet what makes Enceladus remarkable is not only what we have learned about it, but the way each discovery opened new questions, as though this small moon were patiently teaching us how to ask better questions about where to look for life, what conditions might sustain it, and how vast and various the universe truly is. The story of Enceladus is not a story of dramatic discovery or sudden revelation. It is instead a story of patience, of incremental understanding, of the gradual turning of a lighthouse beam across increasingly dark water, illuminating more and more with each rotation. It is a story that asks us to slow down and consider the evidence piece by piece, to sit with the mystery before rushing toward conclusion. And in many ways, it is a story that mirrors the process of falling asleep itself, a slow descent into a world governed by different rules, where what seemed solid reveals itself as far more fluid than we knew, where safety and strangeness exist side by side, and where we must learn to be comfortable in uncertainty. There is something peculiar about learning a world in the dark, about knowing that somewhere beyond the reach of our sun's immediate warmth, beyond even the outer planets most of us learned in school, there exists a small sphere of ice so completely wreathed in mystery that it has only recently begun to yield its secrets. Enceladus, just one more name in the catalogue of moons that orbit Saturn, yet it harbours perhaps one of the most profound questions we can ask of our solar system. Is life possible there? Not in some distant future, not on some exoplanet we cannot yet see, but here, now, hidden beneath kilometres of ancient ice, in a place we can actually study and explore. That possibility alone seems to warrant our attention. If you have found yourself drawn to the particular kind of wonder that comes from contemplating these distant, quiet corners of our planetary neighbourhood, those worlds that exist in a kind of serene obscurity, slowly turning in the darkness, while we here on Earth go about our lives largely unaware of them, then perhaps you might consider joining us for more of these slow, patient journeys into the unknown. We exist in an age where the universe is finally becoming legible to us in ways it never was before, where spacecraft sent decades ago are still sending back whispers of discovery, where a small icy moon can suddenly transform our understanding of where life might be found. Each episode is designed to unfold at the pace of genuine curiosity, to linger on the moments of discovery, to sit with the questions that don't yet have answers, to explore not just the facts about places like Enceladus, but the quiet, patient work of human beings who have devoted their lives to understanding them. There is a particular kind of relaxation that comes from surrendering to that kind of learning, from allowing your mind to drift alongside the story of a world so distant that it takes hours for light from the sun to reach it, yet so intricately connected to our own questions about existence. Now, to understand how we came to know Enceladus at all, we must venture backward in time, not across space, but through history. We must imagine a night in England in the year 1789, when the world was far smaller and the cosmos far less populated in the human imagination than it is today. The discovery of Enceladus unfolds not in a grand observatory under a celebrated night, but in the quiet English countryside on the 8th of August, 1789, when an amateur astronomer named William Herschel stood at the eyepiece of his own handmade reflecting telescope and caught something most observers had missed entirely. He was not searching for a new moon specifically that evening. He was observing Saturn itself, that magnificent ringed planet which had captivated astronomers for centuries, watching its dance and its slow turning in the heavens. The telescope Herschel had built with his own hands was remarkable for its time, a 7-foot instrument made of polished metal and glass, crude by modern standards, yet sensitive enough to reveal details invisible to the naked eye, to pierce deeper into the darkness than anyone before him had managed. Picture, if you will, the scene in its quietness. A man standing in the cool night air, his eye pressed against the eyepiece, the rest of the world asleep or indifferent, only the vast sky and the mechanism between his eye and the stars. Saturn would have appeared not as we see it now in photographs, that perfect, sharp disk floating in black, but as something softer and more veiled, a pale yellowish world ringed with that famous ellipse, and around it other moons already known to science, already named and catalogued and absorbed into the mathematical tables of the age. Yet on this particular night, something new emerged from the blur and grain of the telescope's view, a faint speck of light that seemed to dance at the edge of Saturn's disk, separate from the known moons, independent in its orbit, small and subtle enough to have escaped notice until that very moment. Herschel was experienced enough to know the difference between an instrumental ghost, a phantom created by the lens itself, and a true celestial object. He observed it carefully, watching its motion, its position relative to Saturn and the other moons. The speck he saw was moving as a moon would move, tracing a path consistent with orbital mechanics, and gradually he became certain that he had discovered something no human eye had caught before, a new satellite of Saturn, unknown to Ptolemy or Galileo or Cassini, waiting in the darkness until the invention of a sufficiently powerful instrument and the vigilance of a single observer brought it into knowledge. This was not an instant of triumph announced to throngs of people, not a discovery made in a celebrated lecture hall before applauding scholars. It was small and solitary, and deeply human, a moment of noticing, of patience rewarded, of seeing what had always been there, but remained invisible until someone looked in exactly the right way. Herschel would record the event in his notes, and his observations would be communicated to the scientific societies of his time, and gradually, over the course of weeks and months, other astronomers would turn their own telescopes toward Saturn and confirm his finding. The new moon would eventually be named Enceladus, after a giant from Greek mythology, and it would enter the long list of celestial bodies known to humanity, catalogued and assigned a place in the order of things. What Herschel could not possibly have known as he stood at his eyepiece in that English night was what Enceladus truly was, that this faint point of light was not merely a barren, lifeless rock, as all moons were then assumed to be, but rather a world containing within its small ice-covered sphere an entire hidden ocean of liquid water, vaster in volume than all of Earth's seas combined, kept warm by tidal forces and internal chemistry that would not be understood or even suspected until nearly 2 centuries after his observation. He saw only a bright dot, faint and distant and silent. He could not know that beneath that icy crust, water and chemicals swirled in darkness, or that in that darkness, perhaps, there might be something that could be called life, though life so alien to human experience that we could scarcely imagine it even now. For now, though, for this moment as we trace the quiet arc of discovery backward through time, we rest with Herschel and his telescope, and that first sighting, a reminder that the greatest revelations often begin not with fanfare, but with simple observation, with someone patient enough to look carefully at what the universe has to offer, with attention turned toward a faint speck of light, noticing that it is there, and wondering what it might be. Imagine, for a moment, something small enough to hold in your hand, yet profound enough to reshape our understanding of where life might flourish beyond Earth. Enceladus is, by planetary standards, delicate. Its diameter measures only about 504 kilometers across at its widest point, a span you could drive in roughly 6 hours if roads existed on the moon itself, or roughly the width of Arizona from one border to another. In the architecture of our solar system, it ranks among the smaller moons, a whisper compared to Earth's own companion. Yet what it lacks in size it compensates for in brightness and mystery. The surface of Enceladus possesses a quality that drew astronomers' eyes from the very first moments of scrutiny. It is brilliantly white, almost luminously so, catching and reflecting sunlight with an intensity that seems to defy the usual dusty, cratered appearance we associate with older, weathered worlds. When light from the distant sun strikes Enceladus, nearly everything that touches it bounces back outward into space. We call this reflectivity its albedo, and Enceladus ranks among the most reflective bodies in the entire solar system, reflecting perhaps 90% or more of the sunlight that encounters it. To understand why this matters, consider how a fresh fall of snow appears brilliant white to your eyes, while a patch of snow that has accumulated dust or dirt over weeks will darken. Enceladus, perpetually, appears as though freshly fallen snow, untouched by age or weathering. This extreme brightness arises from a covering of water ice, clean and relatively recent in a geological sense. The ice is not uniformly ancient. Some regions of Enceladus show impact craters that have persisted for billions of years, their walls still casting sharp shadows into valleys below. Yet other regions appear strikingly smooth and young, their surfaces renewed by processes that scientists would spend decades trying to fully understand. It is as though the moon possesses two faces, one ancient and pocked with the memory of cosmic collision, and another fresh and unblemished, suggesting that something beneath the surface has been resurfacing portions of Enceladus throughout much more recent times. The composition of this icy shell is not pure water alone, though water dominates. Spectroscopic observations, the analysis of light reflected from the surface, reveal that the ice contains other substances as well. Carbon dioxide exists frozen into the crust in some places. There are hints of ammonia ice in certain regions, compounds that lower the freezing point of water and suggest complex chemistry occurring in whatever reservoir lies below. The surface temperature hovers around 40 Kelvin in sunlit regions, plummeting to even colder depths in shadow, a place where water exists in its most crystalline, most stable form. And yet, here lies the profound gentleness of Enceladus's riddle. The moon is small, distant, and impossibly cold. Its surface should be static, unchanging, a frozen museum of its early history. The fact that parts of it appear youthful, that new ice continually covers and renews the landscape, that plumes of material erupt from its poles, these observations forced scientists to ask a question that would take years to answer. What, beneath that brilliant white armor, could possibly be warm enough, active enough, to generate such geological youth in a world so far from the sun? The answer would eventually reshape our entire conception of where in the cosmos liquid water might be hiding, waiting to be discovered. But before that revelation arrived, scientists had only the visible evidence. A small moon, bright as fresh snow, with patches of terrain that seemed far too young to be real, and the growing certainty that something profound had been overlooked, something hidden beneath the ice. The Voyager spacecraft, those twin pioneers launched in the late 1970s, carried with them instruments both for mapping and for wondering, and as they began their long arc through the outer solar system in the early 1980s, Enceladus waited in orbit, patient and small, a world that had been discovered but scarcely seen. When Voyager 1 swept past Saturn in November of 1980, it gathered its first close images of this tiny moon, and what emerged from that grainy data, transmitted across the vacuum as a stream of ones and zeros, was puzzling in a way that would occupy the minds of planetary scientists for decades. The photographs were coarse by modern standards, nothing like the crystalline detail that would come later, but they revealed something peculiar about Enceladus's face, something that seemed to defy the simple logic of a small, dead, frozen world. Here was a body scarred and cratered in some regions, marked with the ancient impacts that should tell the story of a world that had been geologically dormant for billions of years. And yet there were places, smooth, unblemished plains that seemed almost pristine, that suggested something else entirely. How could a moon so small, so far from the warming sun, possess surfaces that looked newly formed? The riddle deepened when Voyager 2 made its own pass just 9 months later, in August of 1981, offering a second set of observations and confirming that what they were seeing was real, that Enceladus was not uniform in age, that its surface told two different stories at once. The craters spoke of antiquity, of a world hammered by meteorites in the distant past, but the smooth terrain whispered of something younger, something that had either erased the older impacts or never formed at all. The initial interpretations were necessarily tentative. Without the ability to know what lay beneath the ice, scientists proposed various mechanisms, perhaps cryovolcanism, the eruption of water or ice instead of molten rock, perhaps internal tidal forces that occasionally warmed and shifted the surface, perhaps simply regions that had been reshaped by the slow creep of ice across geological time. But there was a quieter fascination beneath these technical discussions, a sense that Enceladus was withholding its true story, that the Voyager images, for all their achievement, had only posed a deeper question. The moon's brightness was striking too. Its icy surface reflected nearly 90% of the sunlight that touched it, making it one of the most reflective bodies in the entire solar system. And this brilliant whiteness, this almost luminous quality when glimpsed in photographs, seemed to hint at a world of perpetual winter and profound stillness. What the Voyager missions could not do, of course, was measure the interior of the moon. They could observe only the surface, that thin skin of ice that Enceladus presented to the cosmos. And so for more than 2 decades after those 2 brief encounters, Enceladus remained a riddle, held at arm's length by the limitations of remote sensing and the vast distances of space. The smooth plains and the puzzle of their youth would lodge themselves in the minds of scientists, a mystery waiting for a spacecraft equipped with more sensitive instruments, more time to linger, more patience for revelation. And that spacecraft was already being designed, even as the Voyagers transmitted their final images home, a mission that would carry instruments of remarkable sensitivity and would eventually orbit Saturn for more than a decade, gathering data that would transform Enceladus from a puzzle into something far stranger and more wondrous than anyone in the 1980s could have imagined. What emerged from those earliest grainy images, however, was something that would puzzle planetary scientists for decades. Enceladus presented a paradox written across its face. The spacecraft cameras had revealed not one uniform landscape, but rather a world of striking contrasts. The northern hemispheres showed terrain cratered and ancient, a surface that appeared to have been frozen in time for billions of years, bearing the scars of countless impacts from asteroids and comets. Yet as the gaze shifted toward the equator and the southern regions, the landscape began to transform. Here lay vast plains of almost unsettling smoothness. Stretching across the surface were regions so young, so geometrically regular, so conspicuously free of the impact craters that should have accumulated over planetary history, that they seemed to belong to a different world entirely. It was as though someone had taken a cosmic eraser and swept clean a portion of this small moon. The Voyager scientists faced a genuine mystery. How could a moon, only about 500 kilometers across, a world you could cross by car in less than half a day, possess both the ancient face of geological death and the fresh countenance of continued youth? The leading hypothesis that emerged during those years, carried forward by researchers studying the data in university offices and observatories, focused on a mechanism that felt almost too elegant to be true. Perhaps, they reasoned, Enceladus harbored internal heat. This heat would need to be substantial, concentrated, capable of driving geological activity on a world so small that it should have cooled entirely billions of years ago. The mechanisms they proposed were subtle but intriguing. Perhaps tidal forces, the gentle gravitational flexing caused by Saturn's immense pull, had been kneading the moon's interior like a baker working dough. Such tidal friction would generate warmth deep within the structure, and that warmth might have resurfaced portions of the crust through cryovolcanism, a process analogous to volcanic activity on Earth, but involving flows of water and ice rather than molten rock. Imagine liquid or semi-liquid water, warmed from beneath, forcing its way upward through fractures in the icy shell, then refreezing on the surface to create those smooth, crater-free plains. The process would, quite literally, erase the record of impact and write a new geological chapter on top of the old one. Other scientists entertained the possibility that tidal heating might have created subsurface reservoirs of liquid water, pockets of warmth and fluidity sandwiched between the rigid icy shell above and the rocky interior below. But the word ocean, the phrase subsurface ocean, remained purely theoretical, almost whispered among specialists, rather than stated as a serious contender. It was speculation, built upon speculation, educated guesses, layered upon educated guesses. The evidence simply was not conclusive. What made the smooth plains so compelling, however, was their very existence as a puzzle to be solved. They demanded explanation. A small icy moon should not display such obvious signs of youth unless something had actively maintained its surface, unless something had kept reshaping and renewing the landscape. Cratering, impact after impact over time, should have buried any smooth terrain under the accumulated record of cosmic bombardment. Yet here it was, pristine and confounding. The scientific imagination seized upon internal heat as the most plausible answer, even as the instruments available at the time could not definitively confirm it. And so throughout the 1980s and into the 1990s, Enceladus occupied an ambiguous place in our understanding of the Saturn system. It was a world of intrigue and incomplete answers, a moon that had revealed enough to raise profound questions but not enough to settle them conclusively. The smooth plains remained one of the great unsolved riddles of planetary exploration, a silent invitation to future missions, a hint that something more lay hidden beneath the frozen surface, waiting for more sophisticated instruments, for closer examination, for the patience of another spacecraft to arrive at Saturn and look more carefully at this enigmatic little world drifting in the outer reaches of the Sun's realm. For nearly 2 decades, those early Voyager images remained the only close look humanity had managed of this small, enigmatic world. Scientists studied them endlessly, in the quiet of their offices and laboratories, turning the puzzle over in their minds, wondering what lay beneath that impossibly smooth ice. But the questions remained unanswered, the mystery patient and deep. Then, in 1997, a spacecraft called Cassini-Huygens lifted away from Earth on a journey that would take it not directly to Saturn, but in a long, spiraling path through the inner solar system. This would not be a rushed voyage. The spacecraft, which carries within it the accumulated hopes and curiosity of thousands of engineers, scientists, and dreamers, would spend nearly 7 years traveling, taking gravity assists from Venus twice and from Jupiter once, each swing around a planet, bending its trajectory slightly, like a stone skipping across still water, each skip carrying it closer to its distant destination. Can you imagine the patience required in such a mission? The spacecraft would travel nearly 3 billion miles in an almost meditative arc through the void. Its instruments lay dormant through much of that time, waiting. The people who built it would grow older. Children born when Cassini launched would be teenagers by the time it arrived. And yet the mission continued, steady and certain, following its predetermined path through the darkness. The quiet of that journey was profound. Between the gravitational assists, Cassini drifted in the near vacuum of space, moving at roughly 40,000 miles per hour, yet experiencing that velocity as a kind of stillness, a smooth gliding through the cosmic silence. It was a journey that embodied one of astronomy's greatest virtues, the willingness to wait, to plan, to trust in mathematics and physics to carry you where you need to go, no matter how long the path. By 2003, Cassini had reached the outer solar system. The Sun, which commands so much of our attention here on Earth, had dimmed to a bright star in the spacecraft's view, and Saturn, that pale beacon toward which Cassini had been traveling for so long, began to grow larger on its instruments, no longer a distant point of light, but a world, a system, a place. The gas giant revealed itself slowly, its rings becoming more distinct, its many moons beginning to appear as separate objects rather than faint smudges of reflected light. What must it have been like for the scientists and engineers who had devoted their careers to this mission, watching their spacecraft finally approach the goal they had pursued for so long? There is a particular kind of tension and wonder in such moments, the knowledge that after all these years of planning, of launching, of traveling through the void, you are finally about to see things that no human eye has ever witnessed with such clarity. In the months before arrival, Cassini began its careful approach towards Saturn. This was not a time of high speed and dramatic maneuvers, but rather one of gentle adjustments, small corrections, a gradual spiraling inward toward the planet and its retinue of moons. The spacecraft was being guided into orbit around Saturn itself, a complicated feat that required precise calculations and careful timing. Cassini would not simply fly past, as Voyager had done decades before, but would settle into a long orbit, becoming, in a sense, a temporary moon of Saturn, a silent observer positioned to study the system for years to come. Enceladus was only one of Saturn's many moons. The system is extraordinarily complex, a miniature solar system unto itself, with dozens of worlds ranging from tiny irregular objects to substantial spheres larger than our own moon. And yet, among all these worlds, Enceladus had been marked on Cassini's journey plan. The mission architects had designed a series of flybys, close approaches that would allow the spacecraft to study this small, bright world in unprecedented detail. It is worth pausing here to consider what makes such a mission possible. Enceladus, at its closest, would still be many thousands of miles away when Cassini passed. Yet from that distance, instruments far more sophisticated than those carried by Voyager would be able to detect things that earlier spacecraft could only guess at. Spectrometers could analyze the composition of the ice and any material ejected from the surface. Cameras could resolve features smaller than had ever been visible. Magnetometers and particle detectors could sense the environment around the moon. As Cassini made its final approach in the summer of 2004, entering into orbit around Saturn, after a journey that had consumed almost half its design lifespan, even before the science could truly begin, the stage was set for a transformation in our understanding of this distant, frozen world. The patient voyage was about to yield its rewards. The questions that had lingered since the Voyager era were about to find answers, though in ways that no one had quite predicted, in discoveries that would prove far more profound and unsettling than anyone had anticipated. The quiet of that long journey through space was about to give way to a different kind of revelation, one whispered in plumes of water and ice, erupting silently from the hidden depths of a small moon orbiting a distant planet. In July of 2005, just 13 months after Cassini had begun its careful orbit through the Saturn system, something extraordinary revealed itself, though at first almost nobody was watching for it. The spacecraft had been designed to study the giant planet itself, its rings, its larger moons. Enceladus, small and distant and already explored by Voyager, seemed like a minor appendage in the mission's grand design. Yet on that summer day, as the spacecraft passed behind Enceladus relative to the Sun, its magnetometer, an instrument designed to measure invisible magnetic fields, began recording something peculiar, a disturbance, an anomaly, a whisper that something beneath the moon's ice was speaking. The data came in fragments, traveling across the solar system at the speed of light, arriving at the Jet Propulsion Laboratory in California as streams of numbers and electromagnetic signatures. And then, in the images that followed, the truth became undeniable. Rising from the south polar region of Enceladus, where the ice was deeply fractured, were towering plumes, vast columns of water vapor and ice crystals shooting hundreds of kilometers into the black. They looked almost frozen in time, yet they were erupting continuously, a geyser on an unimaginable scale, and they were real, they were there. The fractures themselves were extraordinary to behold. Long, narrow cracks etched across the South Pole like tiger stripes. Scientists would come to call them exactly that, tiger stripes. Running parallel to one another, dark lines against brilliant white ice. Where did they come from? What force could cut such precise, deliberate marks into a world so small? The fractures were warmer than the surrounding ice, slightly warmer, but still far below the freezing point of water by Earth standards. Yet from within them, from the darkness between those striations, the plumes emerged. Layer upon layer of crystalline ice and vapor, fading upward into the thin Saturnian light, dispersing into space like the breath of something alive. To the scientists who had spent years studying grainy Voyager images, this was revelation. The smooth plains they had puzzled over decades before, those young, unblemished regions that seemed impossible on such an ancient world, suddenly made sense. Something had resurfaced them. Something was still reshaping the moon. Something was moving beneath that ice shell, heating it, fracturing it, forcing water upward and outward, in a process that would eventually reshape the entire landscape. The plumes themselves were not continuous streams but rather intermittent jets, strengthening and weakening as the moon moved through its orbit, responding to gravitational forces that squeezed and released the interior in a slow, rhythmic pulse. And think of what those plumes contained, not merely water vapor, but ice particles large enough to see in the images, and within them, chemical signatures that would take time to fully understand. The plumes were sampling the interior of Enceladus directly, delivering to Cassini's instruments samples that had risen from deep below, samples that would eventually tell a story of hidden heat and hidden water, of a moon that was not geologically dead at all, but rather alive with internal processes. The tiger stripes themselves seemed to be the arteries through which this hidden world expressed itself, thin openings in the crust through which the interior was constantly renewing itself, constantly revealing its secrets to those patient enough to listen. The moment of discovery, in retrospect, was less a sudden flash of understanding and more a slow unfolding. The first confirmation came not from dramatic revelation, but from careful analysis, from specialists examining the data from multiple instruments, from the slow process of scientific consensus building around an extraordinary fact. Yet there was also an undeniable moment of wonder when the meaning became clear. This little moon, passed over as a mere curiosity, was shouting across the void. This little moon was telling the solar system that it harbored mysteries within. And once that realization took hold, once those plumes were confirmed and photographed and measured, the entire understanding of Enceladus transformed. A geologically active world, a world with internal heat, a world with something moving beneath the ice. The South Polar region became not a quiet, frozen region, but the most dynamic, most fascinating place in the Saturnian system, the place where the interior was most directly visible, where the boundary between what lay hidden and what lay exposed had become impossibly thin. What could possibly warm an ocean buried beneath nearly 100 kilometers of ice, in a place so distant from the sun that solar heat is practically meaningless? The answer lies not in the warmth of our distant star, but in the patient, relentless embrace of Saturn itself. And this is where the physics becomes something almost like a lullaby of gravitational force and planetary motion. Imagine for a moment the intricate dance that Enceladus performs as it orbits Saturn. The Moon is caught in an elliptical path, not a perfect circle, but a gently elongated orbit that carries it closer to Saturn at one point and farther away at another. As Enceladus swings through this orbit, it experiences something called tidal forces, the uneven pull of Saturn's gravity on different parts of the Moon at different times. Picture the giant planet's gravity reaching out across the darkness, tugging harder on the side of Enceladus that faces it, then gently releasing that grip as the Moon swings away. And then, moments later, the pull comes again. This perpetual flexing, this rhythmic squeezing and releasing, happens billions of times over the Moon's history. And with each gentle compression and expansion of the rocky interior, friction builds. Rock grinds against rock, water presses against stone, and the accumulated effect of countless tiny movements generates heat deep within the Moon's body. This is tidal heating, one of the most elegant mechanisms in planetary physics, and it works silently, persistently, asking nothing but patience. The tidal heating is concentrated most powerfully near the south pole of Enceladus, where the ice shell is thinner, where the flexing of the Moon's interior is translated most directly into motion in the layers above, and beneath that south polar region, the subsurface ocean begins to warm. Water molecules, normally content in their liquid state, start to move faster, their thermal energy increasing degree by degree. The pressure from the overlying ice shell and the rock below keeps this water from simply evaporating into vapor, but something far more dramatic is about to occur. What happens as this water grows warmer and warmer, as it approaches the boiling point while still confined by enormous pressure? The water seeks out any weakness, any crack or fissure in the rock and ice that might offer an escape route. And Enceladus, for all its small size and ancient appearance, is not a stable, frozen monument. The tidal stresses that create the heat also create fractures. The south polar region is carved by long, dark lines called tiger stripes, fractures that run parallel to one another like scars across the ice. These are not static features. They open and close with the rhythm of the tides, breathing in their own slow way. When the fractures open, pressurized, superheated water rushes upward from the subsurface ocean. The pressure that has kept it liquid suddenly drops as it approaches the surface, and water that was liquid at the ocean floor explosively transforms into vapor and ice particles. This is geyser formation, the same principle that creates the famous geysers of Iceland or Yellowstone, except here, the driving force is not the sun's heat filtering slowly into the ground, but the crushing gravitational embrace of a giant planet operating on a moon 1 billion kilometers away. The plumes that erupt from these fractures are prodigious. They tower hundreds of kilometers into the thin atmosphere above Enceladus, fountains of water and ice particles shooting skyward with such force that some of the material escapes the Moon's gravity entirely and drifts outward into the Saturn system. The water particles that comprise these plumes are cold when they reach space, frozen solid by the vacuum and the cold of the outer solar system. Yet they carry with them the signature of what lies beneath, a message from that hidden ocean about its temperature, its composition, and the processes that occur within it. Consider the elegance of this system. Saturn's gravity, patient and constant, provides the energy that powers these eruptions. The Moon's interior, flexed and heated by forces that have operated for billions of years, stores that energy and releases it in dramatic bursts. The subsurface ocean, protected from the vacuum of space by its ice shell, remains liquid because of this deep internal heat, creating a stable environment that persists regardless of the sun's fading light. And all of this unfolds in silence, invisible to any observer until the Cassini spacecraft happened to be nearby, with instruments sensitive enough to detect it. The warming is not uniform throughout the ocean. The hydrothermal activity is concentrated, likely occurring in specific regions where the thermal energy from the moon's interior meets the water most directly. These would be the ocean floor regions beneath the thinnest parts of the ice shell, where the path between the heat source and the water above it is shortest and most direct. This concentration of warmth, this creation of thermal gradients and chemical gradients within the ocean, is precisely what might foster interesting chemistry and, potentially, biological activity. But for now, the physics is the point. The physics is the steady, patient mechanism by which a small, distant moon in the outer solar system maintains a liquid water ocean in the depths of space, powered by gravity, sustained by friction, announced to the universe only by the delicate plumes that carry its secrets outward into the darkness. What the Cassini team realized in those first moments of detection was that they were watching something far more profound than mere surface activity. The plumes themselves were the announcement of a hidden world, but proving that world existed required a different kind of listening, one that involved not eyes, but the delicate mathematics of gravity itself. Imagine trying to detect the presence of water beneath a frozen surface by measuring the faintest tug of its weight from hundreds of thousands of kilometers away. That is what the scientists at NASA and the European Space Agency attempted, and in doing so, they unveiled one of the solar system's most precious secrets. The breakthrough came through what is called gravity mapping, a technique so subtle and precise that it borders on the miraculous. As Cassini orbited Saturn and its moons in different configurations, the spacecraft's trajectory, its path through space, was ever so slightly altered by the gravitational pull of Enceladus below. These changes were infinitesimal, measured in millimeters per second, yet they were real and they were measurable. Radio signals sent from the spacecraft to Earth could be analyzed to detect these tiny variations in velocity, and those variations could be translated through careful mathematical analysis into a map of what lay beneath the ice. The crucial insight was this: liquid water is denser than rock. If Enceladus were simply a solid sphere of frozen ice and stone, its gravity would follow one pattern. But if there existed a vast ocean of liquid water between the rocky core and the icy crust, the distribution of mass inside the moon would be different. It would generate a gravitational signature distinct and unmistakable. The scientists compared the actual gravity measurements to predictions based on various models of Enceladus's interior, asking themselves again and again, does this match a solid moon, or does this match a moon that harbors an ocean? When the numbers were analyzed and cross-checked, the answer arrived with quiet certainty. The gravity data revealed that Enceladus was not a solid frozen sphere. Instead, the moon's mass appeared to be distributed in a way that was only consistent with a vast subsurface body of liquid water, likely covering the entire globe beneath the ice shell, perhaps 50 to 80 kilometers below the frozen surface. The ocean was there. It had been there all along, invisible, pressing against the underside of that brilliant, reflective crust. But gravity measurements alone, while compelling, told only part of the story. There was another way to listen for the ocean's presence, and this method revealed something even more intimate about Enceladus's hidden world. If you imagine a spinning top that wobbles as it rotates, you are beginning to grasp the principle. A solid, rigid moon should spin with perfect regularity, its rotation as stable as a gyroscope. But if the crust is separated from the core by a layer of liquid, the crust can move slightly out of sync with the interior. It can wobble. It can slip. Cassini's imaging instruments, working over years of observations, detected precisely this kind of wobble in Enceladus's rotation. The moon's axis of spin shifted by fractions of degrees relative to what the mathematics predicted for a solid body. This wasn't a dramatic or visible effect. You would never see it with your eyes. Yet it was undeniable when the precise measurements were compiled. A solid moon cannot wobble in this way, but a moon with a liquid ocean beneath its crust, that wobble becomes not merely possible but inevitable. The crust and the ocean are not locked together in rigid unity. They are separated. They move with slightly different rhythms. Think of what this means. The brilliant, frozen surface of Enceladus, that reflective shell that caught our attention in the first place, is not directly connected to what lies beneath it. It floats, in a sense, upon an ocean of liquid water. There is a disconnect, a slight but meaningful freedom of movement between the world that faces the vacuum of space and the world hidden below. The ice is not anchored to bedrock. It is supported by something fluid, something capable of flowing, something capable of harboring processes and possibilities unknown. When these lines of evidence were woven together, the gravity anomalies, the rotational wobble, and confirmed against the evidence from the plume composition itself, a consensus emerged among planetary scientists. Enceladus possessed a global subsurface ocean, not a local sea, not a collection of isolated pockets of water, but a planetary-scale body of liquid water encircling the moon like an invisible halo. Some estimates suggested it contained more water than all of Earth's oceans combined, held between a rocky core perhaps 100 kilometers wide and an ice shell that varied in thickness from place to place. Thinner at the South Pole, where the plumes erupted, thicker elsewhere, always pressing upward against the frozen boundary above. This discovery transformed how scientists understood not only Enceladus, but the potential for life-bearing worlds throughout the cosmos. An ocean beneath the ice meant insulation from the harsh radiation of space. It meant pressure and stability. It meant, most intriguingly, the possibility of interaction between the liquid water and a rocky core below, a meeting point between two different geological environments that, on Earth, had proven uniquely conducive to the emergence of life itself. When Cassini's instruments analyzed the composition of those plumes rising from Enceladus's south pole, something remarkable began to emerge from the data, a chemical signature that would reshape how we understood the moon's hidden interior. The samples contained far more than simple frozen water vapor. Embedded within that escaping material were salts, sodium chloride, and potassium chloride primarily, the very compounds you might find dissolved in Earth's oceans. But their presence here, so far from our world, in a plume erupting from beneath an icy crust, suggested something deeper still, something warm and chemically active occurring in that distant ocean floor. Alongside the salts, instruments detected particles of silica, silicon dioxide, in its various crystalline forms. Silica particles are not typically found in quantity in simple freezing water, or in the bland planetary dust we might expect from a dead moon. Their abundance in the plumes pointed instead to a specific and very particular process, one that occurs when liquid water, heated to considerable temperatures, flows through rocky material and dissolves minerals from it. This is not passive chemistry. This is the signature of something very much alive with thermal energy, of water doing what hot water does when it interacts with stone. Think of how minerals dissolve into a natural hot spring on Earth, how that process transforms plain water into something rich with dissolved compounds. That same dance was occurring, we came to understand, far beneath the ice of Enceladus. And then there were the organic molecules, carbon-bearing compounds, carbon dioxide, methane in small quantities, and more complex organic substances emerged in the chemical analyses. Organic molecules, it's crucial to understand, are not inherently alive. They are simply carbon-based compounds, and carbon is perhaps the most promiscuous element in the cosmos, forming bonds with nearly everything it encounters. Yet their presence in measurable quantities raised a quiet, profound question. Where do complex organic molecules come from in an icy moon's interior? How do they form and persist in a subsurface ocean? One possibility, and here we're on the threshold between what we know and what we carefully infer, involves what scientists call primordial organic compounds, molecules that formed in the solar nebula billions of years ago and were incorporated into Enceladus as it first coalesced. These ancient organics, preserved in the icy moon's interior, might be detected in the plumes as trace ingredients. But another, perhaps more tantalizing possibility involves the ongoing chemistry of hydrothermal environments themselves. In Earth's deep-sea vents, where superheated water rich in hydrogen and other reactive compounds flows through ancient rock, quite complex organic molecules are spontaneously generated through purely chemical pathways, with no biological activity required. Might the same be true in Enceladus's ocean? The combination of these chemical signatures, the salts, the silica, the organic compounds, began to paint a portrait of the moon's hidden seafloor that grew progressively more coherent with each new analysis. Picture, if you will, a subsurface ocean not so different in principle from Earth's own oceans, but one kept liquid by tidal friction rather than by atmospheric pressure and solar heat. Picture rocky material on the ocean floor and water percolating through it, heated by internal radioactivity and by the constant flexing of the moon's interior as Saturn's gravity tugs and releases, tugs and releases. That water, growing hot, dissolves minerals from the rock, sodium and potassium compounds that were already there, silica-bearing minerals that weather and dissolve. Some of those minerals come free and are later carried upward in the plumes. Some of the dissolved material might undergo further chemical reactions in the warmth, perhaps generating new organic compounds or concentrating ancient ones. This is not speculation running wild. This is the application of known chemistry to known conditions, the drawing of reasonable inferences from detected data. And it's worth pausing to notice how carefully the evidence accumulated, how many independent lines of inquiry converged on the same conclusion. The salt content implied a rocky ocean floor in contact with liquid water. The silica particles implied heat and chemical weathering of that rocky material. The organic molecules implied both the preservation of ancient compounds and the possibility of ongoing chemical synthesis. Each ingredient, considered alone, was suggestive. Considered together, they painted a remarkably coherent picture, one that geochemists recognize as characteristic of a very specific phenomenon, the signature of hydrothermal activity, of water and rock in intimate, ongoing conversation, separated by great distances from the sun, yet chemically alive and generative nonetheless. What lies at the bottom of Enceladus's hidden ocean, in the absolute darkness where water meets rock, remains one of the most tantalizing questions in planetary science, yet the answer may be written in the chemistry already captured in those rising plumes. Deep within the Saturnian system, beneath nearly 100 kilometers of ice, water and stone have been in contact for billions of years, and where that contact occurs, at the ocean floor itself, something remarkable may be happening. On Earth, in the deepest trenches of our own oceans, there exist places of profound strangeness, where sunlight has never penetrated, where the pressure would crush most surface creatures instantly, and yet life flourishes in abundance. These are the hydrothermal vents, towering chimneys of rock and mineral that release superheated water rich with chemicals from the Earth's interior. Around these vents, in water that should by all logic be lifeless, communities of microorganisms thrive without any dependence on the sun. They draw energy instead from the minerals themselves, from the chemical potential stored in hydrogen sulfide and methane and iron compounds, in a process so alien to most earthly life that scientists initially thought they were observing some kind of error or artifact when they first discovered these ecosystems in the 1970s. The parallels to Enceladus are, at first, merely chemical whispers in the data, Those particles of silica found in the plumes, microscopic spheres of silicon dioxide, are particularly telling because on Earth, silica particles of similar size and composition are produced when hot, slightly alkaline water meets cooler ocean water, which is precisely what happens at the base of hydrothermal vents. It is as though Enceladus's plumes are carrying a signature, a faint but unmistakable message written in mineral language. The presence of salt, too, suggests water that has been in prolonged contact with rock, leaching minerals away slowly over eons. Consider the scenario scientists have come to regard as plausible, even likely. Imagine the ocean floor of Enceladus, a landscape as unimaginably distant from our world as any place we can conceive, yet governed by physics entirely familiar. Rocky core meeting liquid water. The moon's interior is slowly cooling, yes, but that cooling is accelerated and sustained by the relentless gravitational kneading it receives from Saturn itself. As Enceladus orbits, it is pulled and stretched and flexed by the giant planet's immense gravity, and this mechanical action generates heat. Some of that heat rises, and some of it reaches the boundary between rock and water. Where does it concentrate most? Almost certainly at the hydrothermal vents. Picture them, if you will, towering structures, perhaps meters or tens of meters tall, composed of mineral-rich deposits precipitated from superheated water. The water inside them may reach hundreds of degrees Celsius, while outside, the ambient ocean water hovers just above freezing. The chemical gradient between the two is vast and energetically rich. Is there a force more fundamental than such a gradient? It is here, in this contrast, that certain microorganisms on Earth have learned to thrive. The comparison is not merely poetic, though there is poetry in it. It is grounded in thermodynamics and biochemistry. If life emerged on Earth in such vents, and many astrobiologists believe it did, then the mere existence of similar conditions elsewhere makes the possibility of similar life not implausible. The ingredients are present in the chemical inventory of Enceladus's plumes. The energy source would be available at those vent structures on the ocean floor. The isolation from the surface, the chemical richness, the sustained thermal gradients, all of it mirrors the conditions that we know can support life without the sun. And yet it is crucial to hold this thought gently, without overstatement. The presence of the right ingredients, the right conditions, the right energy sources, these are necessary, but not sufficient. Life requires not just a welcoming environment, but a way to begin, a chemical pathway that leads from non-living to living. On Earth, we have only one example of life, and it is the product of 4.5 billion years of history on a world uniquely rich with complexity. To find life on Enceladus would be extraordinary, not because it would be impossible, but because it would tell us that life-bearing chemistry, or even life itself, is not the singular exception that our world represents, but rather something more common, more inevitable. The hydrothermal vents at the base of Enceladus's ocean remain, for now, a hypothesis grounded in chemistry and planetary physics, but unobserved, unvisited, still dwelling in the realm of careful scientific speculation. Yet each particle of silica in the plumes strengthens the case that beneath the ice, in the dark and cold and crushing pressure, a world of geological activity persists. The vents may indeed be there, releasing their mineral-laden waters into the surrounding ocean, creating oases of chemical richness in an otherwise sparse environment. Whether those oases harbor life remains among the deepest questions we can ask of our solar system, not because the answer is obvious, but because finding it would mean expanding the known universe of the living beyond anything we have yet discovered. Now, here is where the evidence begins to whisper something more remarkable still, and where we must tread carefully between what we know and what we hope, because inside that dark ocean beneath the ice, something extraordinary might be happening. Life. Not as we have found it on Earth, not in the forms we know, but perhaps in forms we have only theorized about, never seen. The question itself is almost too delicate to speak aloud. Could there be living things in the waters of Enceladus? Microbes, single-celled organisms that might thrive in the darkness and cold where sunlight has never reached. It is important to say this plainly. This is not yet confirmed. Scientists do not yet have proof. What they have instead is something more subtle. They have possibility. They have the chemistry and physics that make such a thing conceivable, that make our minds settle into wondering rather than dismissing. Think about what we have found in those plumes: salts, silica particles so fine they suggest heat and water interaction on the ocean floor far below. Organic molecules, carbon-based compounds that are often associated with life, though they can also form through purely chemical processes. These ingredients alone do not tell us life is there. They tell us the conditions exist. The recipe is present. But a recipe in an empty kitchen does not bake a cake. What would convince us? What would we need to find to know, truly know, that life has bloomed in that hidden sea? First, we would need to detect biosignatures, chemical fingerprints that life leaves behind. On Earth, living things produce methane. They create certain ratios of organic compounds that are too organized, too complex, to have assembled themselves by chance alone. We would need to find something similar drifting in the plumes of Enceladus, a chemical signature that speaks of metabolism, of organisms eating and breathing and growing. But even that is tricky. Even a biosignature is not absolute proof. Not until we hold it in our hands and study it in ways we cannot yet do from across the solar system. The Cassini spacecraft, magnificent as it was, could taste the plumes in passing. It could sample them on its sensors and relay data across billions of miles. But it could not cultivate them. It could not grow them in a laboratory. It could not watch them reproduce. For true confirmation, for the kind of certainty that would satisfy science, we would need to bring samples back to Earth. Or, more ambitiously, we would need to send a lander through that ice shell and directly sample the ocean itself. Imagine a small robotic explorer melting through kilometers of ice, reaching the waters below, and searching there for evidence of cells, for fossils perhaps, for the structure and chemistry of organisms adapted to an alien ocean. This is why the conversation about Enceladus has become so urgent among planetary scientists, not because they are certain life is there, but because the consequences of not looking, of not checking, seem increasingly hard to bear. If life began in two places in the same solar system, in Earth's oceans and in Enceladus's hidden depths, then life might be common. It might bloom wherever the conditions permit. It might fill the universe. And yet we must live with this uncertainty for now. We must hold the question without a definitive answer, the way one holds a small stone in the palm of the hand, turning it over to catch the light, feeling its weight, but never quite knowing what it is made of until you can study it closely. The evidence leans toward possibility rather than proof. The chemistry suggests hospitality rather than barrenness, but life, if it is there, remains silent. It does not broadcast its presence across the void. It simply persists, perhaps, in the cold and darkness, unknown and unwitnessed, waiting for someone, something, curious enough to look. And there exists, orbiting Saturn in a gossamer spiral that few eyes ever notice, a ring so faint and so vast that for decades astronomers scarcely acknowledged it was there at all. This is the E-ring, the outermost and most delicate of Saturn's ring system, a structure so ethereal that even in photographs from the Cassini spacecraft, and it appears less like a solid object and more like a whisper of frozen dust suspended in the vacuum. What makes the E-ring remarkable? What connects it so intimately to Enceladus and transforms a small moon's internal turmoil into visible planetary architecture? is that this ring is being continuously replenished and renewed by the very plumes erupting from that distant ice world's south pole. Consider for a moment the sheer elegance of this connection. Every second, day and night in perpetuity, billions of tons of water ice and vapor pour upward from Enceladus into space, escaping the moon's gravity entirely and beginning their slow drift into the Saturnian system. Some of these particles rise high enough and fast enough that they enter orbits around Saturn itself, becoming part of a dynamic, ever-shifting cloud that encircles the entire planet. The E-ring exists not as a permanent structure, but as a kind of continuous conversation between moon and planet, a feathering of material that would quickly dissipate and settle inward were it not for Enceladus constantly pumping fresh ice into the void. The particles that comprise the E-ring are remarkably small, many of them mere micrometers across, each one a fragment of that subsurface ocean we glimpsed in the plume chemistry, flung outward and scattered by the radiation and solar wind that permeate the Saturn system. They drift in orbits that take them far from Enceladus, spreading gradually outward to form a tenuous disk that extends for hundreds of thousands of kilometers. In fact, the E-ring is so sparse that if you could somehow travel through it, you would notice almost nothing. The particles are so thinly distributed that they would never actually collide with a spacecraft or pose any danger. Yet collectively, they form a visible structure, an artifact of ongoing geologic activity, a ring that exists only because a small moon continues to breathe out its interior into space. What does this tell us about Enceladus itself? What does this gossamer architecture reveal about the nature of the moon we have been considering? The very fact that the E-ring exists and persists suggests that the plume activity we have been discussing is not a temporary phenomenon, not a brief episode of outgassing that might fade and leave the moon dormant. Instead, the presence of the E-ring, its visibility, its consistent brightness and composition, points toward a process that has been unfolding on geological timescales, thousands or perhaps even millions of years. The ring is a chronicle written in ice, a patient record of Enceladus's interior furnace working steadily across vast stretches of time. Scientists studying the E-ring with data from Cassini and earlier spacecraft have found that the particles composing it have distinctive chemical signatures that match remarkably well with the material detected in the plumes themselves. They contain salts, silica, and the subtle traces of organic compounds that suggest hydrothermal processing. This match is not accidental. It is evidence of provenance, proof that the particles in the ring genuinely did originate from Enceladus and have traveled from that moon to their current orbits, carrying with them a chemical fingerprint of their birthplace. The E-ring is also not uniform in its distribution. The densest concentrations of material are found close to Enceladus's orbital path, which makes intuitive sense. The closer you are to the source, the thicker the stream of particles flowing outward. But as you travel outward from Enceladus and Saturn, the density gradually thins. Over time, these particles experience subtle gravitational influences and the pressure of solar radiation, effects that cause them to spiral slowly inward towards Saturn, or, occasionally, outward into the deeper solar system. This means the E-ring is in a constant state of flux, with old particles gradually departing and new particles arriving continuously from the plumes, maintaining a kind of dynamic equilibrium, a steady state that depends entirely on Enceladus's continued outgassing. One might wonder whether other moons in the Saturn system have rings around them, whether they too feed into this interplanetary architecture. The answer is no, or at least not substantially. The E-ring is unique to Enceladus, a distinction that speaks to the unusual intensity and persistence of Enceladus's plume activity. Other icy bodies in the Saturnian system are either geologically quiet or lack the particular combination of subsurface ocean, tidal heating, and active outgassing that Enceladus possesses in such remarkable abundance. Enceladus, in this sense, is a moon that is quite literally reshaping the structure of Saturn's environment, leaving a trail of its own substance orbiting the planet, visible across time. There is something deeply poetic about this arrangement. Saturn's rings are famous, studied since Galileo first glimpsed them through a primitive telescope centuries ago. Yet most people think of Saturn's rings as ancient structures, perhaps remnants of an ancient collision or a moon that was torn apart by gravitational forces. The E-ring reminds us that at least one ring in this system is actively being created, renewed, refreshed with each passing day, a ring that would not exist without the living geology of Enceladus unfolding beneath its icy crust. The E-ring is not a relic, it is a present-tense phenomenon, a manifestation of current activity, a ring that exists because something is still happening, something is still alive on that distant moon. The story of Enceladus does not end with discovery and measurement. Even as Cassini's final transmissions reached Earth in 2017, even as the spacecraft made its lonely plunge into Saturn's clouds, scientists were already imagining what might come next. The future of our relationship with this small, luminous moon remains unwritten, a series of hopeful proposals, each one carefully designed to answer questions that cannot quite be settled from a distance, no matter how precise our instruments become. One of the most compelling concepts involves flying directly through the plume itself. Picture a spacecraft approaching the South Polar region, threading its way through those towering fountains of ice and vapor, collecting particles in flight. This is not mere fantasy. The architecture exists on paper. Such a mission would taste the plume directly, gathering organic molecules and chemical signatures that have traveled all the way up from the ocean below, unchanged by the harsh light of space. The particles would be captured in specialized collectors, preserved in their original state, and then analyzed aboard the spacecraft or transmitted back to Earth in the form of detailed chemical fingerprints. What would we learn from such a sample? The composition would tell us whether the hydrothermal chemistry truly matches what we theorize. It might reveal unexpected organic compounds or confirm the presence of chemical energy sources that microbes might exploit. But such a mission exists only in proposal documents, in the careful calculations of mission designers who understand the challenges of navigating a small moon's active region, the risks of ice particle impacts at high speed, the engineering required to preserve delicate samples through the violence of the encounter. Another vision reaches even further. Imagine landing on Enceladus itself, not a simple touch-and-go maneuver, but a sustained presence on the ice. A lander descending onto one of those smooth plains, perhaps near the tiger stripes, instruments slowly waking to sample the surface directly. Ground-penetrating radar could peer down through kilometers of ice, mapping the structure of the shell, searching for thin spots where the ocean might be closer to the surface. Seismic sensors could listen to the moon's interior, detecting the subtle rumbles and reverberations that might reveal the depth and extent of the liquid water beneath. Such a lander would be extraordinarily challenging to build and deploy. The energy requirements alone are formidable. Solar panels would capture almost no useful power in the distant sunlight of Saturn's realm, so any lander would depend on radioisotope power sources or advanced battery technologies. The surface is cold, hostile, and untested by human machinery. Yet the science potential is profound. A lander could drill into the ice, gathering samples from depth. It could remain on the surface for months or years, conducting experiments that a flyby spacecraft simply cannot accomplish. And if some future mission were to deploy not just a lander but a subsurface probe, an ice melting or ice drilling robot that could tunnel downward, then we might actually reach the ocean itself. To sample water from the subsurface ocean directly, would be to move from inference to verification, from measurement to direct contact. Even more ambitious concepts exist in early conceptual stages. Some scientists have proposed small submarines or submersibles that might one day explore the Enceladus Ocean from within, diving beneath the ice shell, following hydrothermal plumes down to their sources on the ocean floor. This is speculation of a higher order, a dream that rests on technologies that do not yet exist in any form, that would require solving engineering problems of staggering complexity. How would a submarine break through kilometers of ice? How would it operate in an ocean of unknown pressure and temperature? How would it communicate with the surface? Yet these questions are being asked, are being discussed in serious forums among serious scientists. That such conversations happen at all speaks to how compelling the Enceladus puzzle has become, how the promise of that hidden ocean has captured imagination and ambition. The timeline for these missions remains profoundly uncertain. Several concepts have been studied by space agencies. NASA's Jet Propulsion Laboratory has examined the plume sampling idea in detail. ESA has considered icy moon missions. The Japanese Space Agency, JAXA, has proposed its own concepts. But funding is limited, priorities shift, and political will fluctuates. A dedicated Enceladus orbiter might arrive by the 2030s if current proposals are approved. A plume sampling mission could follow in the 2040s or beyond. A landing might not occur for decades after that, if it occurs at all. These are not firm schedules but hopes, sketched on the timescale of missions that take a decade or more from conception to launch, and several more years to traverse the solar system. The Cassini mission itself required more than 20 years from initial concept to final orbit insertion at Saturn. The next chapter in Enceladus's story will be written slowly, across a time span that exceeds the career of any single scientist who studies it now. What makes these proposals worth imagining, worth maintaining in the realm of possibility, is that Enceladus poses questions that observation from afar may never fully answer. We can measure the plumes, we can analyze the composition from distance, we can model the physics and refine our understanding. But some questions demand a presence, demand that we send machines to the place itself, to the strange, frozen world where water erupts upward from darkness below. To confirm whether life exists there, to detect even the simplest microbial organism, would almost certainly require the kind of direct investigation that only a physical mission can provide. And that is why, even in the face of enormous technical and financial challenges, the proposals continue to be refined, to be discussed, to be kept alive. Enceladus has revealed so much already. It seems to promise that more lies waiting, if only we can find the means to look more closely. And yet, as we sit with the image of these plumes reaching endlessly upward into the Saturnian night, it becomes hard not to wonder whether Enceladus stands alone in this hidden abundance, or whether our solar system harbors other such worlds, other secret oceans buried beneath silent shells of ice. The truth, as it often does in science, invites us outward rather than inward, to compare, to measure, to recognize patterns in worlds that seem at first glance to be utterly distant from one another. Consider Europa, that distant moon of Jupiter, barely larger than Earth's own moon, yet suspended in an ocean so vast that it may contain more liquid water than all of Earth's seas combined. Europa has long held the imagination of planetary scientists, a world whose icy crust bears long, curving fractures that speak of internal stress, of tides pulling and releasing. When we look at Europa, we see something familiar in its youth, in the evidence of internal geologic activity. Yet Europa's ocean remains utterly sealed from our instruments, hidden beneath perhaps 20 kilometers of impenetrable ice. We know it is there, inferred from the way Jupiter's gravity tugs at the moon's interior, from subtle measurements of its magnetic field, But we have never peered into those depths the way Cassini allowed us to glimpse into Enceladus's waters through the window of the plumes. Europa is, in many ways, Enceladus's older sibling, larger, more distant, colder, more mysterious. Where Enceladus has cracked open to show us its ocean, Europa guards its secrets still. Then there is Titan, Saturn's largest moon, a world so unlike any other that it scarcely seems to belong to our solar system at all. Beneath Titan's thick, murky atmosphere of nitrogen and organic haze lies not just an ocean, but an ocean of liquid methane and ethane, those simple hydrocarbons that on Earth exist only as gases or liquids at extraordinarily cold temperatures. Titan moves to a different rhythm entirely. Its subsurface ocean is indeed thought to contain water, perhaps even water-ammonia mixtures that remain liquid far below the freezing point where ordinary ice would form, and yet that water is overlain by seas and lakes of liquid methane on the surface itself, evaporating and raining down in methane storms unlike anything on Earth. Titan is simultaneously more alien and more lifelike than Enceladus, a world with genuine weather, with dunes of organic particles, with chemistry cascading across its frozen terrain. When we search for habitability, Titan reminds us that life as we imagine it might wear disguises we have not yet learned to recognize. What draws these three worlds together in our minds is a fundamental question that has reshaped planetary science over the past 2 decades. The question of where, in the vast cold darkness beyond Earth's warm sun, liquid water persists in sufficient quantity and chemical complexity to possibly nurture life. Once we thought that life required proximity to a star, that it needed light to photosynthesize, or warmth radiating directly from a host sun. These moons have taught us something quieter and more profound, that life might arise anywhere there is liquid water, chemical energy, and time enough for chemistry to become biology. Enceladus speaks to us in a particular voice within this chorus. It is small enough to have cooled entirely, and yet its ocean remains liquid, not from some distant primordial heat, but from the present-day friction of tidal flexing. Its plumes carry organic molecules and minerals that suggest chemical gardens on the ocean floor, where heat rises and minerals precipitate, where simple compounds might recombine into something more complex. The ease with which we can sample its water, simply by flying through the plume, makes Enceladus a kind of accessible entry point into the study of subsurface oceans. It is the most welcoming of these hidden worlds, the one that has most freely shared its secrets with us. Europa, by contrast, will likely demand of us greater patience and more technological sophistication. To reach its ocean, we must either melt through 20 kilometers of ice or land on its surface and conduct chemistry in conditions of extreme cold and isolation. The Europa Clipper mission, now en route, will orbit Jupiter and fly past Europa many times over the coming decade, measuring the moon's properties, refining our models, preparing the way for eventual landing attempts. But for now, Europa remains the mystery within the sealed chamber. Titan appeals to us differently still. Its thick atmosphere actually shields us from some of our instruments, yet it has also revealed through radar imaging vast dunes, cryovolcanoes, and landscape features that suggest an active world, reshaped continuously by its methane cycle. A mission called Dragonfly, a rotorcraft that will fly through Titan's methane-hazy skies and touch down to gather samples, is now being developed for a journey that will not begin until the 2030s. And so we have 3 moons, 3 oceans, 3 different pathways to potentially habitable worlds. Enceladus, the small moon that opens its depths freely. Europa, the sealed enigma orbiting the giant Jupiter. Titan, the organic-rich world with its methane seas and nitrogen sky. Each represents a different flavor of the same underlying truth, that our solar system may not be a dead and dormant place, but rather a garden of possibilities, where liquid water and chemical complexity exist in places we once thought were frozen, barren, and eternal. To study one is to ask questions about all of them. To wonder about one is to wonder about the universe's capacity to harbor life in forms we have not yet imagined. And so we return, once more, to that simple image, the plumes. Vast geysers of water and ice and salt, rising from the depths of a small moon that orbits at the edge of our solar neighborhood, impossibly distant, impossibly patient, erupting silently into the vacuum where no one is there to hear them. No one, that is, except the instruments we have sent to witness. The Cassini spacecraft captured them. The Hubble Space Telescope has traced their signatures in the ultraviolet light. And yet, to any observer standing on Saturn itself, looking down at this tiny moon, these geysers might appear as nothing more than a faint suggestion of brightness near the South Pole, a whisper of activity on a world that seems, at first glance, frozen and still. There is something profound in the patience required to understand Enceladus. William Herschel saw it first by candlelight and telescope more than 2 centuries ago, a mere dot of reflected starlight. He could not have imagined what lay beneath that icy crust. The voyagers glimpsed it in passing, seeing smooth plains that confused the scientists of that era. And then we waited. Years and years, Cassini circled Saturn, drawing closer and closer, until finally those plumes erupted into view, and suddenly the small moon became one of the most intriguing places in our solar system. But even that discovery was not an ending. It was, rather, an invitation to deeper questions, and those questions remain, as they will for decades or perhaps centuries to come. Consider the nature of distance itself. Enceladus orbits at roughly 1,200,000,000 miles from the Sun, far enough that solar radiation offers little warmth to the surface. Yet beneath that frozen shell, in an ocean we cannot see and have never touched, water moves. It circulates. It touches rock. It carries within it the chemistry of life as we understand it, or at least the building blocks of such chemistry. How strange that the farther we journey from the Sun, the more we discover about the possibility of living worlds. How the most distant places, it seems, might harbor the most delicate activity. This is not tragedy, though it bears a certain melancholy. It is rather the quiet revelation of how the universe distributes its wonders, not always where we expect them, but patient, persistent, enduring in the dark. The plumes themselves drift silently. No sound carries in space. No roar accompanies those towering jets of water vapor and organic compounds as they rise hundreds of miles above the surface, spreading their contents across the rings of Saturn, feeding the E-ring with material born from the moon's living interior. In our minds, we imagine some kind of cosmic fountain, something dramatic and loud. But the actual eruptions occur in perfect silence, in perfect cold, witnessed only by the faint instruments of our spacecraft and by the distant stars. There is a kind of grace in this silence, a kind of dignity in the idea that these processes continue whether we observe them or not, whether we care or not, whether we understand them or not. What draws us to places like Enceladus is, perhaps, not so much the hope of finding life, though that remains, quietly, a possibility worth exploring. Rather, it is the simple mystery of existence itself, the evidence that worlds beyond our own are active, are changing, are responding to forces we are only beginning to comprehend. Every plume that erupts carries with it a story of heat and pressure and time, a story written in the language of physics and geology and chemistry. We are only just learning to read that language, and perhaps that is enough. Perhaps the act of patient attention, the long, slow process of gathering data and forming careful hypotheses, of sending our instruments to distant moons and waiting for their messages to return across the void. Perhaps this itself is a kind of meditation. The future may bring new missions. Spacecraft may yet fly through those plumes, may sample their contents in more detail, may land on the ice and drill deeper into the mystery. Or those missions may not come for decades, or centuries, or perhaps not at all. The plumes will continue regardless, erupting from the south pole of Enceladus, rising into the darkness, falling back to the surface, or drifting into orbit to join the rings. The ocean beneath will continue its slow circulation, its exchange with the rocky core below, its patient accumulation of chemistry. The moon will continue its orbit, flexed by Saturn's gravity, heated by the friction within, alive in ways we are only beginning to recognize. There is something restful in understanding that this process does not depend on our attention, does not accelerate or slow based on our curiosity. Enceladus has been erupting geysers for billions of years, perhaps for the entire history of the solar system. We arrived only recently, with our instruments and our questions. We observed and we marveled, and we began to build theories about what might be possible there. But the moon itself goes on, indifferent, perfect in its distant orbit, enduring in its silence. Imagine, if you will, the plumes as they rise at this very moment. Somewhere in the darkness beyond Neptune's realm, beyond the reach of the sun's warmth, they are rising. Water molecules born perhaps in the rocky mantle of Enceladus, heated by tidal friction, escaping through cracks in the ice, rising into the vacuum. Some will be captured by Saturn's gravity and fall back. Others will escape into the rings, to become part of that faint light you might see through a telescope if you knew where to look. Still others will drift into the deeper darkness, eventually to be lost in the vast emptiness of space. Each molecule carries no awareness of this journey, no sense of beginning or ending. It simply moves, rises, falls, transforms. It participates in processes far larger than itself, and in that participation, it is complete. There is a kind of peace in contemplating the plumes this way, as part of a system so vast and so patient that individual moments of observation seem almost insignificant. And yet, those moments matter too. Our discoveries of Enceladus matter. The curiosity that drove us to send our instruments across billions of miles of space matters. The patience required to wait for answers, to remain uncertain, to live with the profound questions that still surround this small moon and its hidden ocean. This matters. And so the plumes continue their silent eruption. The water continues its ancient circulation. The moon continues its dance around Saturn. At great distance, in the cold and the darkness, life continues in ways we are only beginning to understand. The universe unfolds, moment by moment, vast and unhurried. And in contemplating it, in allowing ourselves to wonder about it, in remaining patient with the mysteries that remain unsolved, perhaps we find ourselves drawing closer, not to the answers we seek, but to something deeper, to an understanding of how small we are and how precious the act of wondering itself has become.